Good morning, everyone. Today, I will be talking about the second law of thermodynamics, one of the most important laws in understanding how energy works in real world systems. While the first law tells us that energy cannot be created or destroyed, the second law explains why not all energy can be converted into useful work. It introduces concepts like entropy, reversibility, and limits of machines such as engines and refrigerators. Now, the very important question is why the second law matters. The second law matters because it defines the direction in which natural processes occur. Heat naturally flows from hot to cold, not the other way around. That's the second law at work. It also sets the efficiency limits for machines and explains why perpetual motion machines can't exist. In short, this law governs energy quality and help engineers design realistic systems. Now let's talk about the Kelvin-Planck statement. The Kelvin-Planck statement of the second law defines the limitation of the heat engines. It states that it is impossible to construct a device that operates in a cyclic process and produces no effect other than the extraction of heat from a single reservoir and the performance of an equivalent amount of work. In simple terms, this means no heat engine can convert all the heat it receives into the work. Some part of the heat must always be rejected to a cooler sink. This statement sets a natural limit on efficiency. Even the best designed engines like steam turbines or car engines cannot be 100% efficient because of this unavoidable heat loss. So, the Kelvin Planck statement reminds us that every real engine must have both a heat source and a heat sink, and that some energy will always be lost as the waste heat, making perfect efficiency physically impossible. The Clausius statement of the second law explains the limitations of refrigeration and heat pumps. It states that it is impossible to construct a device that operates in a cycle and transfers heat from a colder body to a hotter body without any external work. In simpler terms, this means heat cannot flow naturally from cold to hot. It requires an input of work. This is why refrigerators, air conditioners, and heat pumps need electric energy to run. The compressor inside does work to move heat against its natural direction, from the cold interior to the warmer surroundings. The Clausius statement sets fundamental limit of refrigeration performance and explains why cooling devices always consume power. It also complements the Kelvin-Planck statement. While that one limits how much work we can get from heat, this one limits how much cooling we can achieve without work input. These two statements may sound different, but they are equivalent. If one could be violated, the other would also be violated. For example, if a refrigerator could transfer heat from cold to hot without work, we could combine it with an engine to make a system that produces work with no heat loss, violating Kelvin Planck. So both statements express the same fundamental truth. These two statements led to the design of a perpetual motion machine, a perpetual motion machine of the second kind, or perpetual motion machine 2. It is a hypothetical device that converts all absorbed heat into work continuously without losses. The second law tells us such a machine is impossible. Real machines always have friction, losses, and some waste heat, making 100% conversion of energy is unachievable. Let's consider a real-world application for case study of a second law. Second law of thermodynamics, we have taken the example of heat engines. Heat engines are practical applications for the second law of thermodynamics. Examples include car engines, steam turbines, and power plants. In all these, heat from fuel is partially converted into mechanical work, while some heat is released to the surroundings. Engineers use the second law to maximize efficiency by reducing waste heat and improving the design. Similarly, we have the real world entity refrigerators, which also follows the second law. The second law also governs the refrigerators and air conditioners. These devices use mechanical work to transfer heat from low temperature regions to higher temperature regions. Understanding this law helps us design systems with better coefficients of performance and lower energy consumption, like modern inverter ACs and eco-friendly refrigerators. Let's look about the role of the entropy and the irreversibility of the reaction. Entropy is one of the most important ideas in the second law of thermodynamics. It is often described as a measure of the disorder or randomness in a system, but more accurately, it represents how energy spreads out or becomes unavailable for useful work. According to the second law, during every natural or spontaneous process, the total entropy of the universe always increases. This means that energy tends to become more disorganized over time. For example, when heat flows from a hot object to a cold one, or when fuel burns, some energy becomes unusable. This makes the process irreversible. You can't make the heat flow back naturally or unburn the fuel. In engineering, understanding entropy helps us analyze efficiency and energy losses. It tells us why no machine or process can be perfectly reversible and why real systems always generate some waste energy. To conclude the second law of thermodynamics, the second law of thermodynamics is not just a theoretical concept, it's a law that governs everything from machines to life itself. It tells us that while energy can change form, it can never be completely converted into useful work. There's always some loss in the form of heat or increased entropy. This is why no engine can ever be 100% efficient and why refrigerators need continuous power to operate. The law also introduces the concept of entropy, which helps us understand the irreversibility of the natural processes. For example, why heat flows spontaneously from hot to cold and never the reverse. In essence, the second law sets the limits of efficiency and defines the direction of all real processes. It forms the foundation for energy, conservation, environmental sustainability, and modern engineering design. So, the second law reminds us that while we can never beat nature's limits, understanding them help us design smart and more efficient systems. Thank you.